So, the first thing that we want to do, the first thing you always want to do is write an equation. And so we have this mercury substance that's going to be thrown on the ground. So HgNO CnO2 going to something. When that goes to something, we have to see what the products are. And so it says, although the real chemical is not that explosive, it does degrade to show, to make the product carbon monoxide gas. So carbon monoxide, and that is gas, plus nitrogen gas, N2, that's a gas, and mercury metal, which is a liquid, so Hg with an L. Now, what we need to do is we can also put an S here. We know it's a solid because it's a crystal that he throws on the ground, a chunk of it. And so what we need to do is we need to balance this equation. And so mercury already balanced, carbon is not yet balanced, so we'll put a 2 right there. Nitrogen is already balanced, and now oxygen is balanced as well. So this is our equation. This is all we need to do from that. And so the question asks, how many liters of gas are formed the instant after the reaction occurs at 106 degrees Celsius and 310 kilopascals of pressure? And so now that we've written the equation, we can continue our list over here. So we have 206 grams right there. And what we need to know as well is the molar mass of HgCnO2, which is going to be 242.6 grams per mole. Grams per mole. And so from this, we can see how many how many moles of this exploded. That's going to be able to translate to the number of liters of gas. And so let's just start there, because we do need the rest of these values. And we're trying to find the liters of gas. So we have PT, we're looking for V, we don't know that. PV equals nRT, we can get N right now. So we'll start with 2.06 grams of Hg. Put something right here so we can tell that that's different. 2.06 grams of Hg. Now, we will go and say that we have the molar mass to get to moles, so that's going to be 242.6 grams for every 1 mole of the Hg, I'm going to say F for Hg fulminate. So HgF for the mercury fulminate. Now, if we look at the equation up here, for every 1 mole of HgF that we have, we're going to make 3 moles of gas. So there is a 1 here and a 2 here. All of these are going to contribute to the number of moles of gas. So for every 1 mole of Hg, we get 3 moles of gas. 3 moles of gas. And we don't care what the identity of that gas is quite yet. And so when we do this calculation, we end up getting 0.0255 moles of gas. And so we can now say that our N is going to be 0.0255. That is our final value. And so even though it's a 2.06 gram chunk, we have relatively low moles of gas. That's because most of the molar mass here is due to mercury, which is quite heavy. Okay, so now that we have this information, we can continue, but let's clean it up a little bit more, so then we can just find the number of liters and we don't have to do much else. So we have 310 kilopascals. Can we use that? Well, yes, we can, because it's not in millimeters of mercury, which means that we can use one of the other values. So this is another value that might be worth memorizing. If we go to our units and we find the kilopascal unit, we can see that 8.314 liters times kilopascals equals over Kelvin moles is very similar to our atmosphere one. Where's our atmosphere one? Which is right there. We have, oh, that's not it. We have, our atmosphere one is down here. Right, liters atmosphere, so it's just liters times pressure over temperature times moles. And so we will use this one right here, 8.314. So our R value, we can keep this in kilopascals. And we'll just use a different R value. R is going to be equal to 8.314 K PA times L divided by Kelvin times mole. All right, and so if we're doing PV equals nRT, we now have our P, we have our T, we have our N, which is moles of gas, and we have our R, and we're just trying to solve for V. So what I'm going to do is I'm going to steal this and copy it, and we're going to paste it on the next page so we have a little bit more space to work. So this is all of our information that we have. We can get rid of this right here because all we need to do now is solve for V. Now, we have PV equals nRT, and we want to solve for V, which means we will just divide by P on both sides. Divide by P, and P, and we end up getting V equals nRT divided by P. Now we can just plug those values in. So we have N, which is 0.0255 times R, which is 8.314, and times T. Oh, we have not converted T yet, so let's go ahead and do that. So if we add 273.15 to this, or just 273, we get 379, which is fine. 379 Kelvin. Okay, so 379 is going to be our next value that we put in. And then our P is going to be the 310 kilopascals that we start with. So we end up with our volume being about 0.259 liters. Okay, so that's our volume of gas that came out of this. So we can answer this. How many liters of gas is 0.259 liters of gas. We want to know what the partial pressure from CO2 is. And so here's how we're going to do this. So the partial pressure from CO2, well, the equation says that for every not CO2. It does say CO2, doesn't it? Okay, it means CO. 2 COs and every 1 N2. There's 2 COs and 1 N2 to make 3 moles of gas. And so what we can do is we can say that 2 out of the 3 moles of gas are CO, which means that the pressure is going to be applied in the same way. So we can say that 2 out of the 3 amounts of pressure, which is 2 out of 3 times 310 kPa, is going to be equal to the partial pressure of our CO value. So our CO, once we do that, is going to be, let's see, what do we have here? the P total divided or times the mole fraction of CO, which is going to be 310 times 0.666 gives us 206.46 kPa from CO. 206.46 kPa from CO. And so we will then take that and give it the correct number of significant figures, which is going to be 3, so that's 206 kPa. And now let's go back. So that's what we're going to have for the partial pressure. It's going to be 206 kPa. What's the partial pressure from CO2? That's that answer. And then what's the mole percent of N2 in the gas? Well, we're going to do the exact same thing. We know that there are 3 moles of gas. So 3 moles of gas. And one of those moles is N2. So it's just 1 divided by 3. The part divided by the whole, which gives us a mole ratio of 0.333 mole ratio of N2, which is, if we multiply that by 100% times 100%, we end up getting 33.3% N2. Okay, so that's how we would answer that one. It's a bit hefty. There's a lot of things we have to plug in and change around. I also used an R value that we haven't used before, but this is how that one would be completed. Okay, so collecting gas over water. So we can collect gas over water, and this is because all liquids, well, really everything, has something called a vapor pressure. A vapor pressure is a constant amount at which the liquid or substance is turning into a gas. So everything pure is going to have a vapor pressure to some degree. For things like metals, that number is incredibly small, very, 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 very small, unless you're something like mercury, which actually does have a high vapor pressure and is one of the reasons why it is so dangerous. Breathing in those fumes is going to be what's dangerous. But the partial pressure of water, and when we're talking about vapor pressure, is only dependent on temperature. So at higher temperatures, you're going to have more volatile water, which means that it's going to have a higher vapor pressure. At lower temperatures, the opposite is going to be true. And so there's, for example, we have a reaction prepared here. So hydrogen prepared by the reaction of zinc and hydrochloric acid is going to be put into an inverted tube right there. And it's going to be initially filled with water. And then the gas collection tube is going to be on the other side. And so the pressure that's going to be in this tube, the P total, is going to be whatever the pressure of the hydrogen is plus the pressure of the water. So the vapor pressure, and that's going to depend exactly on what the temperature of that water is. Okay. And so this chart gives you a very good example of exactly what those pressures are. So above the surface of water at 0 degrees, there is going to be a pressure of that water evaporating. Even though it's at 0 degrees, which is the freezing point of water, it's going to be evaporating at about 4.6 millimeters of mercury. At 100 degrees, you get a whole atmosphere of millimeters of mercury, and that's because it is boiling. It's becoming a gas. It's at equilibrium with the air, is what that means. All right, so this is an example problem. Go ahead and give it a shot, and then we will go over it. Okay, so to do this, what we have to do is see what it says. So the gas is collected over water. Determine if the mass of hydrogen collected is 156 milliliters, and determine the mass of hydrogen collected if 156 milliliters of gas is collected at 19 degrees Celsius, and the total pressure is 769. So the first thing we need to do is see where that is. So at 19 degrees, we have 16.5 millimeters of mercury due to water. So the P total is equal to pH2 plus pH2O. And P total we know to be 769. And we also know that we will have that equal to the pressure of, this is going to be the pressure of H2. But we also know that for the pressure of water, that we have 16.5. So 16.5 millimeters of mercury plus the pressure of H2O. And so from this, we can determine that the, not H2O, it's going to be just H2. The pressure due to just H2 is going to be 769 minus 16.5 is going to equal the pressure of just H2. And so this value ends up being 752.5 millimeters of mercury. And so from there, we can calculate the mass. So we can use PV equals nRT, and we're going to solve for moles, because once we solve for moles, we can convert that to mass. The other thing we need to do is, we know that this is 19 degrees Celsius, so we'll have to convert that to Kelvin. So that's going to be our P is going to be 752.5. Our V is going to be 156 milliliters, so 0.156 liters. Quick conversion there. Our T is going to be 19 plus 297, and that gives us 292.15. And our N is what we're looking for. The other thing we need to do is, pressure is in millimeters of mercury, and so we are going to have to convert millimeters of mercury to, we're going to have to convert millimeters of mercury to atmospheres first. So that's going to be 752.5. We will take that and divide it by 760. 760.5 divided by 760 for every 1 atmosphere. That gives us 0.990 ATM. And so all we have to do is solve for N. So we'll rearrange this equation to solve for N, which gives us PV divided by RT equals N. And we'll just plug in the values. So P is going to be 0.990. Multiply that by our volume, which is 0.156 milliliters. And we will divide that by R, which we have determined because we converted to atmospheres, we can use 0.0821. And then for our T, we'll use the value that we calculated before. That is 292. And we can just use the, we can get rid of the 0.15. It's okay, because all of the other values are going to have 3 significant figures. And that is going to leave us with a value of 0.00641 moles of H2. Now, we will then take the find the number of grams by dividing it by 1 mole and multiplying it by the molar mass of 2.02 grams, which gives us a value of 0.0130 grams of H2. And that is our answer. And so, if we take a look and see what was done, this is exactly what occurred. So we have, I'll leave that one there. We have the total pressure being equal to the partial pressure of H2 and the partial pressure of H2O. And so in order to get H2 by itself, we will subtract the amount of H2O from the total pressure to give 752 millimeters of mercury. Then convert that to atmospheres, so we have something we can use this R value with. We also have to convert Kelvin to Kelvin, and we can convert to liters as well from milliliters. And then we will solve for PV equals nRT using the values that I discussed before, canceling out all units that will be contrasting, and we'll be ending up with 0.0641 moles. Finally, we will go to convert that to grams in the exact same way that was discussed before. Now remember, the reason that we are not going to change the amount of milliliters is because any kind of gas is going to take up, if you put two gases in the same container, they will take up the entire container together. Okay, so let's move on to another topic called kinetic molecular theory. So this is also called kinetic theory, and basically what it is telling you about how gases exist. So I previewed this a little bit, but basically it's saying that gases consist of molecules in constant random motion. So what that means is that, let's say that you have some sort of vessel. And we'll put some different atoms in there. I'll zoom in. When you have some atoms in a vessel of gas, then these atoms are going to be traveling at different speeds in random motion. It doesn't matter where they're going or how fast they're going. Well, those things are going to be related to the temperature. How fast they're going is going to be directly related to the temperature. But otherwise, it is impossible to tell where they're going to be going, and they're just going to be bouncing around. Every time these gas particles hit the surface of the container, which they are doing at very, very high speeds, and then they bounce off of it, this is a collision, and this collision is the basis of what constitutes pressure. So it's this gas molecule hitting the side of the container, causing a little bit of force, which is the idea of pressure. And so, because we are saying that all of these gases are molecules in constant random motion, we can apply a equation to deal with them. So what this is saying that the kinetic energy, that's E subscript K, is equal to 1/2 the mass times the velocity, or the speed, which is usually measured in meters per second, squared. So we'll square the meters per second, multiply it by the mass, and then by 1/2, and we end up getting the kinetic energy. And so these are the postulates, Dalton's postulates, that he came up with this. So number 1 says that gases are composed of molecules whose size is negligible compared to the average distance between them. What that means is that if you have this container, then the size of the atom is very, very, very small compared to how far away they are. That means that they are not in contact with each other, really. The second one is that molecules are going to move randomly in straight lines in all directions at various speeds. So it's just random. They just go all over the place until they make contact with something and do what's called an elastic collision, which we will see in just a second. the forces of attraction or repulsion between molecules in a gas are very weak or negligible except when they collide. So that means that we haven't talked about intermolecular forces much yet, but things that have charge, so something like a plus and a minus charge, are going to be attracted to each other, right? Whereas things with a plus and a plus are going to be repelled from each other. And so what this is saying is that we can assume that these forces do not matter. The only ones that do matter are when they actually smack into each other, these molecules. Okay, the fourth says when molecules collide with each other, the collisions are elastic. So elastic means that no energy is lost. And so we'll get into that in just a second. But basically, the collisions are elastic. And we can also say that the average kinetic energy of a molecule is proportional to the absolute temperature. So these things are vibrating around, and depending on what temperature you have them at, that's how fast they're vibrating. This is one of the reasons why at 0 Kelvin, there is no movement. That's the reason why we use Kelvin for this. At 0 Kelvin, there should be no movement at all, and so we should see nothing occur with those. And so let's talk about elastic collisions. So an elastic collision is one where no kinetic energy is lost. The collision on the left is going to cause the ball, it's going to hit the ball. This ball hits this ball hits this ball, and then this ball hits the final ball, resulting in all of the energy from that was being transferred from one to the other. Meanwhile, these stay relatively in the same place. This is an elastic collision because no energy was lost to the balls that are present at the center. This is called a Newton's cradle. And so we can derive each of the laws from those postulates. So for the ideal gas law, we can say that the pressure is equal to is proportional to the frequency of the collision times the average force of that collision. So this is what I was saying. If you have the surface, how often these molecules hit that surface and how hard they hit the surface, I'll make a real big arrow to show that, is going to be proportional to the pressure. So if they hit it harder, harder and more often, then your pressure is going to go up. The average force depends on the mass of the molecule. So if you have a heavier molecule, a heavier atom, whatever you have, then that is going to increase the amount of pressure. And so we call we can call the mass m and the speed u, and we can say that the momentum is the mass times the velocity, or the speed. Speed and velocity are the same thing. So velocity. I might say those interchangeably. So that's something good to know. But mass times speed or velocity is going to be proportional to the pressure. So the frequency of these collisions is proportional to the average speed as well. And the number of molecules is going to be inversely proportional to the volume. I know that's a lot, but what that's saying is that as the volume goes up, the pressure is going to go down. As the number of molecules goes up, the pressure is going to go up. And as the speed goes up, the pressure is going to go up. Anything that is not not 1 over that variable means that the pressure is going to increase, which means that as the mass increases, so does the pressure, and as the speed increases, so does the pressure. And so we can say that the number of moles, let's say, it doesn't matter if it's molecules or atoms or what, times the mass, times the speed, squared is going to be proportional to the pressure and the volume, because volume was 1 over v over here, which means we have to multiply by v on this side to get it over there. The average kinetic energy of a molecule of mass m and the average speed is u, and the average speed is u is 1/2 of m times u squared. Thus, we have proportionality between pressure and volume according to the average kinetic energy of the molecule. However, the average kinetic energy is also proportional to the temperature. So P and V, the kinetic energy is going to increase as temperature goes up, and that makes the pressure and the volume increase. Number of moles also can increase, which is going to increase the pressure and the volume. If we are to put in something to cancel out all the rest of the units, like R, then we get back our initial ideal gas law, PV equals nRT. And so let's talk about molecular speeds. So according to kinetic theory, molecular speeds are going to vary widely. And so this is going to be a distribution. Let's see, there is one, yes. Okay, we'll get to that in just a second. But this distribution is going to depend on the temperature. And so it's going to increase as the temperature increases. And then we also have this term, the root mean square of the molecular speed. This is a way to try to get an average speed of all of those molecules. So it's an average molecular speed equal to the speed of a molecule that has the average molecular kinetic energy. So if you have a population, a ton of different atoms, and they're all going at different speeds, then we use the root mean square value, which is this, 3RT over molar mass. This is molar mass, is going to be whatever speed we need. This is also a good point to write out in case it's been a while since you've taken algebra, but the square root symbol can also be represented as a 1/2 to the power of 1/2 symbol. So that is something that is important. Okay. So when we're applying the equation, we're going to use consistent units. This is just like for PV equals nRT. We do the exact same thing. But 8.31, we've seen this before, right? Let's go back real quick to the problem before this. That is going to be 8.31. 8.31, that's our R constant that had the units kilopascals times liters over Kelvin mole. Now the units, instead of being 8.31 or kilopascals, we have kg, kilograms. I'll do it so they're the same size. Kg times meters squared per second squared divided by, times Kelvin times moles. And so this is just another way for us to use R, but it does have the value that we used before. So all of the things should cancel out, but these are going to be the units that we need. I believe actually this is going to be kilograms meters squared. I think that the type got mixed up with this, but I think it's this. Kilogram meters squared per second squared times Kelvin times moles. And so that should be the units. This would be in parentheses right here. Okay, so these SI units are what we're going to use. Temperature is going to be in Kelvin. M with the smaller m in this case means the molar mass, but this is in kilograms per mole. So usually this is going to be grams per mole, but now we're using kilograms because the units here are kilograms and the units here are moles. Okay. So there was a guy named Maxwell, and he was doing some predictions on these gases. But basically, this is what it's saying. So if we go back here, we can say that the distribution of the temperature ranges is going the speeds is going to be dependent on the temperature ranges. And so that's what we're showing here. So at 0 degrees, this is what the expected distribution is. At some of the atoms are going to be at 0, very few. Some are going to be around 4,000 meters per second, but the majority are going to be right in the center, around maybe 1,500 meters per second. If you increase the temperature, then the range of the gas molecule speeds is going to increase as well, and so you get an average of about 2,500, wherever the top is. But the range is much larger. Now, instead of kind of having an asymptote or going to 0 at 4,000, this is going off the page. It's going to be increasing quite a bit. Okay, so if we want to determine the root mean square speed of O2 molecules in a cylinder at 21 degrees Celsius and 15.7 atmospheres, we're going to use this equation. So the first thing that we want to do is we're going to convert to Kelvin. So we have this right here. So 21 plus 273. 21 plus 273 is going to be 294 equals 294 Kelvin. And so we actually don't care about the pressure because pressure is not going to be one of the values in here. We could solve for U as well using the pressure, using one of the previously discussed equations, but we don't really care about that right now. What we do care about is this. So we can say that U equals our new R constant, which is 8.31 kilogram meters squared per second squared Kelvin mole. So that is going to be 3 times our new R, which is 8.31. And we'll multiply that. I'll do kg times meters squared over seconds squared times Kelvin times mole. And we'll multiply that by our temperature, which is 294 Kelvin. Now we have the number of we have an O2 molecule. So O2 is going to be 15.99 times 2, which is equal, this is the number of grams per mole. 15.99 times 2, which gives us 31.98 grams per mole. Now, what we can do is we can take 31.98 grams and we can convert that to kilograms. So there's 1,000 kilograms. In fact, I will even use a different unit. I'll use 10 to the negative 3. 10 to the 3 grams in 1 kilogram. And so when you divide by a 10 to the third, you get 31.98 times 10 to the negative third kilograms. And so that's what's going to go on the bottom of this equation. We have 31.98 times 10 to the negative 3 kilograms. And so now we can make sure that all our units cancel out, kilograms cancel out, our Kelvin is going to cancel out, and we are left with our moles, and that is on the bottom, kilogram per mole, my mistake. So moles cancel out, and so all we're left with is seconds squared per meter squared, and that should be a tip-off that we haven't done the square root yet. So we'll do the square root, and that's going to get rid of those, and we're going to be left with U, which is going to be in meters per second. And so we're doing the exact same thing. 32.0 is the same as 31.98 pretty much. It's just rounded. We have kilograms, we're canceling out. Kelvin, we're canceling out. Moles, we're canceling out. And then we're left with just seconds and meters. Meters squared and seconds squared, and that's going to be taken care of by the 1/2 exponent, which is equal to, taking the square root of something, we end up with 479 meters per second. So this is a red herring. We didn't need this at all. Okay, so let's talk about another property that gases have. So we have diffusion here. A gas is able to spread out through another gas and occupy the same amount of space. So if you have 1 liter of N2 and you have 1 liter of O2, for example, and you put them both in the same container, that is a 1 liter container, even though you started with 1 liter of N2 and 1 liter of O2, you still have 1 liter of N2 plus O2, even though it is 2 separate liters. If you had these in different containers and you added them both into this 1 liter container, they're both going to take up the same amount of space. It's a little confusing, but let's see what happens here. So concentrated aqueous ammonia in the beaker evolves ammonia gas into a glass tube, which contains a strip of wet indicator paper. The molecular view, in the molecular view, there are only nitrogen and oxygen molecules in the air surrounding the indicator paper. The indicator is going to change color as the ammonia diffuses upward into the air. So this is a closed container that is not, the volume is not changing on this. However, nitrogen is not basic, which means it's not going to change that, oxygen is not basic in the water, so it's not going to change the pH paper. But over time, the amount of NH3, the ammonia that is present in the water, is going to go up and into this container. It's going to diffuse in there without changing the volume of the container. Okay, so we have diffusion, where you have a gas going into the presence of another gas, and effusion is something similar. But this is basically when you have a gas that is going to be leaving a container. So effusion is when you have, let's say you have a tiny pinprick in a balloon. The gas that can escape is going to do so out of that pinprick, right? That is effusion, those gas molecules leaving. Okay, so we can also quantify effusion using Graham's law of effusion, and this is saying that the rate of effusion of molecules is equal to the square root of the molar mass in kilograms per mole, divided by that value. And so as the molar mass increases, you're going to get a slower rate of effusion. And so if we want to calculate the rate of effusion, the ratio of effusion rates of molecules, let's say that we have a container like so that has CO2 and SO2 in it. The only thing we really need to know is the molar masses, because the rate of effusion is going to be equal to the molar masses divided by the molar masses. And so this is going to be the only variable that we use to solve this. And so we'll take, to calculate the ratio of the rate of effusion, we will take the rate of effusion of one substance and divide it by the rate of the effusion of another one. So that's going to be, put parentheses so you can see what's going on a little better, and I'll even put a bar across so that it's even clearer. But this is the first equation. So the rate of effusion of 1 over the molar mass of CO2 and 1 over the molar mass of SO2 can then be collapsed into a single equation where the molar mass of SO2 divided by the molar mass of CO2 and then taken to the 1/2 power, the square root, is going to give you, once we plug in those values, a 1.21, which means that CO2, which was on the top right here, is going to diffuse 1.21 times faster than sulfur dioxide. And so, yeah, all you have to do is plug in the molar masses. You can see how these are just in grams per mole. It doesn't matter because all of these values are going to cancel out. And kilograms per mole and grams per mole, the only difference is that you would have to divide by 1,000 for both of those. So that would cancel out as well. So it is okay when we're using the effusion rate, Graham's effusion law, that you can use kilograms per mole or grams per mole. Either one's fine. Okay, so let's take a look at this setup real quick. Go ahead and take a look at it and see if you can answer this question here. Okay, so what we'll say is that for helium, the molar mass of this is 4. For argon, the molar mass is 40. And so when we're using rate equals 1 divided by the molar mass, the square root of the molar mass, what we will do is we'll do 1 for helium. So rate, and then I'll put HE down here, is going to be equal to 1 divided by the square root of 4, which is equal to 1 divided by 2, which is equal to half. And then we have the square root of 40 for the other one. So that would be rate of AR equals the 1 divided by the square root of 40, which is equal to 0.158. So this is equal to 0.5, and that one is equal to 0.15, which means that helium is going to have a higher rate. Helium has a higher rate, and that's because its molar mass is lower. And so that is exactly what you see. So helium will reach the end first because it has a smaller molar mass. If we wanted the argon to reach the end of the long tube at the same time as helium, what experimental condition, that is, you cannot change the equipment, so we couldn't make this just like a shorter thing over here. That wouldn't work. What could we change, though, that might make that happen first? I'll give you a second. Go ahead and think about it. All right. So what I would do, if you... this is going to be the answer. So if you were able to open the valve at different times, opening argon first is going to give it more time to reach the end of the tube. The other thing that you could do is you could heat that end, because heat is going to be directly related to the kinetic energy of the bulb, and so it should make those things move faster. Okay, so this is the part where I'm not going to cover it a ton, because to actually go over the real gases and the nuances behind them, you need to know differential equations. And I'm going to be honest, I didn't ever take that class, so I can't help you too much with this. But we can talk about what this means. So we talk about ideal gases a lot. We can use PV equals nRT, and this is the ideal gas law. An ideal gas is an imaginary gas that is basically like what these gases would... They seem to act like this around temperatures that human beings are used to. So that's how we're going to... that's how we are able to like quantify them, measure them, and all that stuff. But if we are talking about real gases, these do not exactly go these do not behave the same way once you put them under a very high amount of pressure. And so after that high amount of pressure, that's when you get some interactions between the molecules in the gas, because they are now hitting each other at enough speed that we can talk about how they are interacting with each other. And so if we look at the values on the left at relatively low differences in pressure, where we have just a 0.1 difference between one tick on this graph and another. That way we have basically very, very similarly behaving gases. They're all going in straight lines. As soon as you crank that Soldier Boy all the way up there, that pressure, it is going to increase the amount of pressure so much that these start behaving no longer linearly. The gases are going to start behaving in very different ways, and so they no longer follow Boyle's law. So at high pressure, some of the assumptions that we have are no longer going to be held true. The volume of the gas of the molecule is not going to be negligible, which means that since these atoms are going to be so close together, they are going to start interacting with each other. And so now their interactions, their volumes are going to be close enough together that they are going to interact. The intermolecular forces are what we're talking about. So the intermolecular forces are between molecules, is what that means, and they're no longer negligible. And so there are many equations that we can use to work this out, but an equation that's similar to the ideal gas law is a little bit different because it has different constants, A and B, to account for deviations from normal behavior. So the term volume becomes volume minus N times B. The term pressure becomes pressure plus N squared A over volume squared. And the values for A and B can be found in table 5.7 in your book. And so this is what we went from PV equals nRT to this absolute monster of an equation. And so table 5.7 is going to have different values for A and B that you are going to be able to see right here. So each of these values is for a specific and common gas. All of these gases are very common, but each gas is going to have its own value for A and B. And so if we were to do this, we would say, let's take a look at that equation. P plus N squared A over V squared. I'm going to just write that down here. P plus N squared A over V squared times V minus N times B equals nRT. And so if SO were an ideal gas, the pressure at 0 degrees Celsius, so that is going to be 273.2, because we now have that sig fig right there, exerted by 1 mole, occupying 22.41 liters, would be 1 atmosphere. If we're using the van der Waals equation to estimate the pressure of this volume of SO2, then we will proceed like this. And so we will plug in all of the values that we have here. So N, we have 1 mole from the previous problem. R is still our gas constant. And keep in mind that this is that crazy equation that I wrote before, just rearranged. We have the temperature, 273.2 in kelvins. And we have the volume, which is now volume minus NB. And keep in mind that A and N come from the values on this table. So for SO2, we have A and B are going to be these values here, 6.865 and 0.05679. And so we have B as 0.5679 here, and A, this is the subtraction of this part, but A is going to be 6.865. All of this is going to collapse to give you this value right here, 0.989 atmospheres. Okay, so that's all that I have for you. This stuff gets very complicated, this van der Waals equation, and so I'm not really going to give this, I wouldn't give this on an exam. I might have given it on homework, but it would definitely be a problem, practice problem. So that is all I have for you. Thanks so much. Hopefully this one isn't too long and you can get through it quickly.